Hello students, welcome to lecture 18 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on optical properties of dielectrics. So, here is the lecture outline. We will see the optical properties of dielectric materials, discuss about the Selmayr dispersion formula, absorption coefficient, properties of bulk crystals. So, let us begin with the optical properties of dielectric materials, and we can see that the real part of the permittivity, which is plotted in blue, typically exhibits a Lorentz line shape around each resonance. So, you can see there is a resonance in the infrared and also in the blue wavelength range. So, this is higher energy, this is lower energy. So, you can say this longer wavelength and this shorter wavelength, and in between this ultraviolet and infrared lies a visible range where the red dashed line, which represents the absorption, or that is basically representing the imaginary part of the permittivity, that is almost 0 or negligible. So, you just have the real part dominating the permittivity in the visible range, right. So, another important thing to see here is that in the case of resonance, so you are basically having the resonance where this particular absorption is maximized, or the imaginary part is maximized, or you can say where the real part undergoes a change in the sign. So, the real part, which is real of epsilon, that is large and positive, as you can see at the low frequency side of the resonance, and then it quickly becomes negative when the frequency is slightly higher than that of the resonance. So, this is where exactly the resonance frequency lies. So, here what again we are actually showing the dielectric function of a typical dielectric material with, you have got the lattice resonance and the electron transition resonance. These are marked as omega 1 and omega 2 respectively. Now, when you get this negative dielectric constant, that is somewhat counterintuitive, because the transparent materials, they have positive dielectric function in the visible range, and when you have a negative value of the real part of the permittivity, that basically implies that the polarization density P, or you can say the electric displacement D in those kind of material at that particular given frequency will be directed in the direction opposite to that of the incident electric field. So, that is how you can understand what does this negative real part of the permittivity mean. Now, the electromagnetic response of a material around the resonance can be seen here. So, this is where the resonance is happening. So, you can actually normalize the frequency axis to the resonance frequency omega naught. So, you can simply write omega by omega naught. So, omega naught is basically your resonance frequency. So, when omega by omega naught equals 1, that is where when this imaginary part is peaking. So, this is where the transition takes place for the real part of the permittivity as well. Now, this particular resonance, you can actually modulate like a spring mass oscillator that can help you in better understanding. So, you have got the electric or the magnetic field this way, and you can have, so we are mainly talking about the electric field, and you can see that the mass or the spring is, or the polarization is also in the same direction. Now, when you are basically here, which is far away from the resonance, in that case the response that you see here will be able to follow the driving force with no delay. However, when you are at frequency which is slightly lower than that of the resonance frequency omega naught, say you are kind of here, in that case what you see that your epsilon or mu for that matter, we are just let's talk only in terms of permittivity right now, epsilon. So, you can see that the mu is basically an increasingly positive function, Okay, that means the response, which is polarization for electric resonances, and if you consider mu, you will talk in terms of magnetization for the magnetic ones. Okay, that is also getting enhanced. Okay, so in this case the response is slightly getting enhanced, which you can see from the mass spring kind of arrangement as well. Now, when you are on the other side of the resonance peak, that is where your response, your epsilon or mu is showing a negative value. That means the response is basically opposite to the driving force, which can be seen here. Okay, so you can write electric field and you will see the polarization is in the opposite direction, or when you talk about magnetic field, you will see the magnetization is in the opposite direction. So, this is what this particular graph basically tells you. Now, the simple square root relationship that we have seen between the refractive index and the permittivity of any material in the frequency domain will just hold good. Okay. So, now if you have a complex permittivity, that means it has got a real and the imaginary part. In that case, your refractive index, the frequency dependent refractive index will also become complex, and you can say it has got two parts. The real part is n prime omega, and then you have an imaginary part which is n double prime omega, and that can be correlated to square root of epsilon omega, which itself is kind of complex, right. So, we understood that the real part of the complex number n omega, this part can be called as the refractive index or index of refraction, the same thing, and the imaginary part n double prime omega is referred to as the absorption index. Okay. So, that basically quantifies the amount of absorption in that material. Now, the simple square root relationship between the refractive index. Okay. So, if you do some basic algebra, you can correlate this equation. Okay, and you can find out how this real and the imaginary part, okay, will be correlated to the permittivity, right. So, some basic algebra can lead you to some useful relationships where you can write down the real and the imaginary part of the permittivity in terms of the real and the imaginary part of the refractive index. Like epsilon prime can be written as n prime square minus n double prime whole square, and epsilon double prime can be written as 2 n prime n double prime. So, in different books they also just write it as n kappa or k. Okay. So, you just need to know the different notations people use throughout the literature, but they all can actually give the same relation between permittivity and refractive index. So, if you do the reverse, that how if you know the real and the imaginary part of the permittivity, from that how can you obtain the real and the imaginary part of the refractive index, you can basically use this particular equation. Okay. Now, we move on to Selmayr formula. So, we will tell you what is the significance of this formula. So, we have seen that the frequency dependence of refractive index, that is n omega, is basically having a very similar kind of plot that is given earlier for the permittivity. So, this is the plot for permittivity, except that there will be some changes, that the curve of the real part of the refractive index will be raised. That means this will have some offset and everything will be a positive value, because in real material you will not see any negative value in the real part of the index. So, in the permittivity part, this part shows negative value of the permittivity, whereas in the refractive index part, this entire graph, the solid graph will be shifted upwards, so that you can avoid the negative value, right. And the imaginary part, that is n double prime omega, is negligibly small, typically of the order of 10 to the minus 5, that is for the common dielectrics in the visible range, which is also can be seen from here, that it is very small, right. So, in such case, the refractive index of this type of material can be modeled in a form which is like this. So, you can write epsilon omega can be written as 1 plus summation over j s j omega j square divided by omega j square minus omega square minus I omega gamma j. So, that basically without involving the imaginary part or the damping constants, right. So, with if you do not take the imaginary part of the damping constants, you can just remove this particular part. Okay. So, the whole thing will look like this then, okay, and you can replace the frequencies with the corresponding wavelengths. So, everything you can convert in terms of refractive index and wavelength, right. So, when you say that there is no damping associated, so the imaginary part also goes to 0. So, you can simply write that this equation, the permittivity will be more or less real. So, when it is real, you can simply write it as n square lambda. You are now moving from the frequency domain to the wavelength domain. Okay. So, you have 1 plus summation over j s j. Now, instead of omega j square divided by omega j square minus omega square, you will simply have lambda square divided by lambda square minus lambda j square. So, they are basically inversely proportional to each other. I am sure you all of you know this particular relation, like f equals c by lambda. So, from there you can convert f is linear frequency. When you do it multiply by 2 pi, you get omega, and from that you can always find out this relation, right. So, some modified form of this Selmayr formula also exists, okay, where you will see that there is an now empirical approximation of n lambda directly provided instead of talking in terms of n square lambda. Okay. So, the power series approximation to Selmayr formula can also be used, where the refractive index n lambda or the square of it can be expressed as sum of power of wavelengths, something like summation over j a j lambda j, okay, where j can be both positive and negative, right. So, this is one standard representation of the Selmayr dispersion formula. N square lambda can be written as 1 plus summation over j s j lambda square divided by lambda square minus lambda j square, right. Now, for characterization of glasses, okay, the equation basically consisting of 3 terms are commonly used. So, you can see that this is a particular graph from the refractive index.info. The red one shows the real part of the refractive index, and the blue one shows the imaginary part, which is basically k. Okay. So, you can find out that if you take a common borosilicate crown glass, which is also known as BK7, so you can use these particular constants B1, B2 and B3, okay, as this, and C1, C2, C3 as this, that will closely model this particular characteristics. Okay. So, for common optical glasses, the refractive index calculated with this 3-term Selmayr equation deviates from the actual refractive index by less than 5 into 10 to the minus 6 over the wavelength range of 365 to 2.3 micron. That means you are having a very good approximation, right. So, this is of the order of the homogeneity of the glass sample. So, you can always try to add additional terms that can make the calculation even more precise, okay. But sometimes you will see the Selmayr equation is also used in 2-term form. So, in that case n square lambda can be simply written as a plus b1 lambda square divided by lambda square minus c1 plus b2 lambda square divided by lambda square minus c2, right. So, you will have only 2 terms here. So, you can see that there is a new coefficient a that is being used as an approximation of the short wavelength, okay, that is like ultraviolet absorption contribution, okay, and that contributions to the refractive index at longer wavelengths. Other variants of the Selmayr equation also exist that can account for the material's refractive index change due to temperature, pressure and any other parameters. So, now let us look into the absorption coefficient. So, for weakly absorptive media, the absorption coefficient, which is alpha, okay, that is regularly used to characterize the attenuation of light when it is propagating through the material. Now, the absorption coefficient is the exponential index that appears in the Beer's law or Beer-Lambert's law, which says that the intensity I naught of the light will decrease exponentially as the light will travel through a medium, and at a distance z it can be calculated as I naught, sorry, this will be I, okay. Yeah, it can be written as I, which is I naught, okay, initial intensity exponential minus, or you can say intensity when z equals 0 exponential minus alpha z, right. Now, since the electric field E changes along the propagation direction, that also follows this function exponential I 2 pi n prime plus I n double prime, okay, z divided by lambda naught. Since the electric field E changes along the propagation direction following the term, so you have exponential I 2 pi times n prime plus I n double prime, that is the complex refractive index, times z divided by lambda naught, right. So, you will see that the intensity, this one is basically proportional to modulus of E square. So, it is easy to say that the absorption coefficient alpha can be connected to the imaginary part of the refractive index, and you can write alpha equals 4 pi n double prime divided by lambda naught, okay. So, typically your absorption coefficient alpha will have the dimension of reciprocal of length, that is centimeter inverse. Now, we will look into the properties of bulk crystals, right. So, optical anisotropy and birefringence are basically intrinsic properties of crystalline dielectrics. So, in an anisotropic medium, which can be a uniaxial or biaxial crystal, okay, the optical response to the electric field is basically direction dependent. So, and we will see that the polarization field P is not necessarily aligned with the external field. So, you have to use tensors instead of scalar values that must be used in the case of electric susceptibility and also the permittivity epsilon. In optical metamaterials, however, when the length scale of the continuous dielectric portion of the unit structure is so small, that means it is very sub wavelength or much smaller than the wavelength of light, then you will see that all the dielectric components will tend to have an amorphous state without any preferred direction. So, therefore, what you can do that in the design and simulation of optical metamaterials, you can assume a scalar value, and that will be typically sufficient for the permittivity or the refractive index of the dielectric constituents. So, as for the nonlinear properties of the dielectrics, they are normally neglected because most of today's optical metamaterials are operated in the linear response region, okay. So, even when the nonlinearity of the metamaterials is included, the nonlinear effects will typically result from metamolecules as a whole plus the surface states of the metallic part, while the nonlinearity of the dielectric itself will play a very minor role, right. So, conventionally the use of metals in optical systems is limited in very few applications, something like mirrors or optical thin films. So, in optical metamaterials you will see that most of the designs which will be studied will incorporate metal in the unit cell of the metamaterial itself, and the sharp contrast between the optical response of metals and that of the dielectric will play an important role in making the metaatom the functional elements. So, most of the compositional units used in making the metaatoms of photonic metamaterials are delicate subwavelength structures, and they contain both metal and dielectric components. And the response of this metamaterial to any electromagnetic field is dependent on its specific architecture of this metaatoms. So, how you design that will tell you how the electromagnetic field is going to behave with that metaatom. Therefore, it is hard to develop a simple and unified method for analyzing the properties of any arbitrary structural unit of a metamaterial. So, you cannot have a simplified generalized theory for all the metamaterial metaatoms, right. However, for composite materials which does not have well structured building blocks, you can use some generalized analytical approach that will give you the luxury of estimating the average electromagnetic response. So, in such randomly structured media, the metal and dielectric components are basically arranged in a disordered fashion. So, the overall optical properties of such a metal dielectric composite will be significantly different to those of its constituent molecules. So, that is where the metal dielectric composites and different mixing rules will come into picture, and we will continue that in the next lecture. So, thank you. With this we will stop here. If you have got any queries, you can always drop an email to this particular email address mentioning the course number and the lecture number, then the course name in the subject line. So, in the next lecture we will see the effective medium theory, which will be a continuation of this discussion. Thank you.